LU with partial pivoting is commonly used to solve large dense systems of linear equations. However, the pivoting part of that often introduces a large amount of communication, which can reduce the performance of the solver. And additionally, it can just limit the amount of parallelism that we're able to exploit. Now, random butterfly transforms are one technique that is used to avoid this pivoting overhead. These are basically random FFT-like transforms that can be cheaply applied, but then the system can be solved without using pivoting. Now, one problem with this RBT approach is that in distributed settings, the butterfly structure doesn't always align with how the matrix is distributed between nodes. And so this can make the communication somewhat complicated and involve working with a lot of partial tiles and some other overheads. So our work generalizes the RBT in a way that we can nicely align that butterfly structure to how the matrix is distributed between processes. And so this, greatly simplifies the communication and reduces some of the other overheads. And with this generalization, we were able to reprove most of the original theory for the RBT and experimentally show that it's about as accurate. And of course, we tested the performance. You can see the solid orange line is the generalized RBT, and the dashed line is the older formulation. And overall, the generalization helps performance, and in some places by a pretty significant amount. Additionally, there's sort of two sets of lines here with slightly different problem sizes. The generalized RBT is fairly insensitive to, changing the size of the matrix by a few hundred rows and columns, whereas the older formulation is very sensitive, and that can make a very large difference in your performance. Overall, we think this is a valuable technique for solving these large dense systems. Thank you.